Hello students, in this video we'll discuss geodesic or normal coordinates on a surface with respect to one given geodesic. So if we're given a surface S, let's consider any point P on the surface. So here's our situation. We have a surface over here. I'm going to think of the unit sphere as our typical example, just because I know what the geodesics are on the unit sphere, right? So there's our surface. And what we're going to do is we're going to fix a point over here. And we're going to draw a geodesic through that point over here. So let's gamma of u be a arc length parameter. That's important. Arc length parameter geodesic. Such that gamma of 0 is equal to p. Okay? So that's our situation. So abstractly what we have is the following. We have a curve gamma over there. There's my geodesic. And this curve gamma of 0 goes to the point p like so. All right? Then what we're going to do is the following. Then we're going to basically like just one sort of direction of our coordinate. So curve is a one-dimensional thing. I need a second direction over here. What we'll do is we're going to let for any v rho v, we define a new curve gamma v, arc length parameter, okay, again that's important. So you have another curve arc length parameter. And what is this going to be? So where gamma v is a geodesic such that two things are true. Set number one, if I plug into this geodesic 0, what I get, I get the original curve at the point v. So if I move down, geodesic down over here to gamma of v, that is equal to this new curve gamma v at 0. That's just for that curve gamma. And second, I want what? The second condition I want is I want these geodesics to be perpendicular to each other, right? I want gamma v dot 0, that vector, to be perpendicular to d by du, d by dv. Yeah. At the point u equals. And of course, what that means over here is d by du of gamma u at the point u equals v is exactly where. So we traverse over this point over here, gamma of v, right? I compute the unit tangent vector, and that give me my u of gamma u at u equals c. Second, this gamma v curve is going to look like this, perpendicular to it. So it's going to be just like this over here. It's going to be this is going to be my gamma v at a different point, say for example at a point u like that, okay? But I know that the tangent over here has to be perpendicular, right? I want to use coordinates now using these geodesics. So what I have is this base geodesic over here, right? It's every point on this, I'm going to draw more geodesics like this. Yeah. What I've done now, I've functionally been able to construct a coordinate system, sort of like almost like a ruled surface, but now the other rulings are going to be geodesics, right? So the rulings now are geodesics. So it's similar to a ruled surface, but now the rulings are geodesics. So what I can do now is define by a parameterization r of u and v to what? Just to be this gamma v of u, okay? So define curves. The parameterization is a valid parameterization of our surface. Of S with first fundamental form. This is the picker over here. The first fundamental form is So the first fundamental form in this parameterization has the form d squared plus a function g of u and v dv squared like so. Excellent. So of course, but now, well, what would U be, right? So if RU, let's look at the, in particular this point, right? So what would R sub U? R sub U is going to be what? It's going to be d by du of this thing, by du of this, and R sub B, then d by dv. That's the question here. So, people. And so now if I let u equal to 0 over here, so I plug in u equals 0 at the point that corresponds to u equals 0, at u equals 0, u equals 0. Okay, so those two vectors at u equals 0, and those vectors are perpendicular to each other, right? So these vectors are perpendicular. So R, U, 0, V, perpendicular to R, V, 0, V. And so since the vectors are perpendicular, that means that the surface patch is well defined. Above the origin, right? So my surface patch is well defined. Right? Whereas time surface patch is going to be ill-defined, but RU, RV are parallel to each other, which you have a one-dimensional reduction of. So in other words, the tropopic can be seen with that. It means the valid parameterization of a surface. Axles. Okay, so for our form of this thing over here, so what would the form be? First of all, this also tells me what? So R, U, 0, V, perpendicular to R, V, 0, V, implies that F in the first fundamental form is 0. That's one condition. So let it look for. Listen, RU. So what would d by du of gamma V of U at U equals 0 be, right? If I do this, if I look at the length of this thing squared, that's going to be 1 because V is an arc length parameter. Is arc length parameter. Beautiful. This is my 1. E is equal to 1. The corresponding form past the idea of this formal period. Now, one in particular about say G0V, for example. Well, that's going to be a derivative with respect to V. Gamma V of U at U equals 0 squared. Okay, great. Of course, this is an arc length parameter with respect to the U parameter. This is also equal to what? That's also equal to U what? That's also arc length parameter. In other words, along that trajectory over here, the metric is conformal to Euclidean space, right? In other words, we have the Gij is delta Ij, this parameters. Ultimate things are saying that Gij, my metric, at 0V is really delta Ij 0V, right? That's so, and we take a more abstract Riemannian geometry class, one whole just coordinates, you're going to see conditions like this, namely that the metric is basically looks like delta Ij near the points of normal or geodesic coordinates, and furthermore the Christoffel symbols to vanish at that point, right? So that's when you take a when you take a Riemannian geometry course, that's the precursor to this in graduate school, then you're going to see this condition sort of written in terms of this, saying that the metric is basically flat near that point, essentially, right? So now I know what? We're Paul now. So if we were Paul, the geodesic equations over here are d by dt by ds, d by dt of f prime plus g v prime half 1/2. Then we'll have a e v u prime squared plus 2f v u prime v prime plus v v prime squared like this, right? So in particular, what do we know? In particular, on this geodesic frame over here, what can we say about this is going to be equal to 0 and this is going to be equal to 0? So what can I say about this GV along the trajectory along 0 be along that at where u is equal to 0 to be 6 over here? Well, the v prime can be equal to 1, right? So GV 0v is going to be what? At the 0 over here, the b is equal to that's bounce on, and I know that g is equal to this thing over here, so that's so g, so it's going to be what? It's going to vanish over here, right? So GV, sorry, GU of course, right? GU of 0 v has to be 0 by this geodesic equation over here. So that's going to be a v over there. So the v component is equal to 0 at that point as well. Excellent. U component over here, if you want to say that the u component is equal to 0, right? So in other words, we get further conditions on GU and GV. So the E equation be what? So I modified this over here. If I can change all these things to u, let's end it to u, change that to u, change that to u, and then we're going to change this over here. So we get the second equation over here. So we want to take about the derivative over here. So let's write that over there. So we have E u prime plus E prime, and then now that's the second geodesic where all these are u derivatives now. So it's a u derivative, u derivative, u derivative. Well, so the E is equal to 1 and the U prime is equal to 0. The F is equal to 0, so the left-hand side is equal to 0. So that implies that 0 is equal to what? 0 is equal to this term over here, 0. This term over here is equal to 0. So that says that, and the V prime is equal to 1. So that says that G sub U of 0V has to be equal to 0, which gives you the conditions on the Christoffel symbols being equal to 0. So these coordinates over here are extremely useful, right? Because, once we have this form over here, if this is the first fundamental form, the curvature is 1 over the square root of G times the second derivative of the square root of G with respect to U 2 times, right? So this first fundamental form in geodesic coordinates allows us to unlock the curvature, the Gaussian curvature, in a very special formula, and allows us to sort of forego doing more tedious calculations in order to find the curvature in terms of a more complex metric structure. So the geodesic coordinates are extremely useful, and we're going to see in further videos how we can write down expansions of these things to relate the curvatures of the areas of geodesic circles to the Riemannian to the Gaussian curvature and to the scalar curvature, and see how those terms pop up naturally in the expansions. Thank you very much.